For the invitation. It's my first DART conference. Very nice to be here. My talk is about a subject which is not, classically connected to differential algebra. Usually it's studied more in in between model theory and logic and their affine geometry. But I'll try to convince you that there are some good reasons to consider this from the lens of differential algebra, differential equations, and that this really yields some new information about some classical problems in this area. So I'll just start by setting up the general subject that I want to study. So the question is about counting rational points on transcendental varieties, but we have to do it with respect to some kind of measure. So the measure we use is the height. So I'll talk only about rational points, and the height we just take to be the maximum of numerator and denominator. We can work with algebraic numbers and then there's various notions of height, so it doesn't really matter. Everything I say will extend to algebraic points for whatever kind of height function you want to use, but just to keep things simple, I will talk about rational points. So if A is any set of real numbers, I define by A of Q all the rational points on it, and I denote by A of QH all the coordinates have height less than h. And then the basic question that we are interested in, that people have been interested in for a long time, is, so can we understand the asymptotic of the number of points of height h as h grows? Of course, it doesn't really make sense to ask this kind of question for a general set. It could be anything, right? You can cook up any set you want. So it should be for some kind of suitable sets in some kind of suitable category. So there's a long story behind this question. It starts before the work of Bombieri-Pila, but I will start my story with Bombieri-Pila. That is a result from '89 that really kicked off this area. So the result of Bombieri-Pila is as follows. You start with a parameterized analytic curve in R2. So just we take an analytic map from the unit interval to R2, and then gamma is the image. So I would be interested in counting rational points on this set, on this curve. So the theorem says as follows. Suppose that this gamma does not belong to an algebraic curve. Okay? Then for any epsilon greater than 0, O of h to the epsilon. So you're less than some constant depending on epsilon and on the set times h to the epsilon. So really the growth of the number of rational points is subpolynomial. It's less than any power of h. Okay, so this is a very general theorem. It works for any analytic curve. You just need to assume that the curve is not algebraic. And this assumption is crucial. So if you just take a curve like x is equal to y, then there will be many rational points, right? For every rational point x, take the same rational point y, then you'll have something like h square rational points of height h. So this assumption is crucial. In fact, Bombieri and Pila studied something slightly different. They studied lattice points, not rational points. So, for example, points with integer entries. And then Pila, 2 years later, extended it to rational points. But really, the key idea was the early work of Bombieri and Pila. So I'll just make a few notes about it. First is that parameterized curve here, because if you take any compact analytic curve, you can parameterize it like this. For example, by blowing up singularities, you can write any compact analytic irreducible curve as a union of images of the unit interval. So the conclusion doesn't work if gamma is algebraic, as I mentioned. And finally, the asymptotic is essentially optimal if you look at general analytic curves. So if you allow yourself if you construct some kind of strange analytic functions with lacunary power series, then you can really you can't get h to the epsilon, but you can get as close as you want to h to the epsilon. So there's no hope of really improving this asymptotic in general. So it's a result that kills this whole question. Okay, so I will not prove this theorem because it would take too long. It's a very nice proof. The general outline of how it works is that first you show that all of the points of this set belong to roughly h to the epsilon curves of some degree depending on your epsilon. Okay, so this is a very nice trick. It's called the interpolation determinant trick that Bombieri and Pila invented. And I strongly recommend that you read the original paper. It's very clearly written. It's something that you can teach to students of calculus, of a first-year calculus. It's really just a nice trick looking at Taylor expansions of these functions and doing some estimates. But suppose that we manage to show this, then the result is automatic by Gabrielov's theorem. So I'll remind you that one of the consequences of Gabrielov's theorem is that if you have a subanalytic family, and you look at the number of points in every fiber, there is a uniform upper bound. So here we have the following family. We have our curve. We intersect it with some algebraic curve of a fixed degree d. So we have this family of algebraic curves. It's a compact family of algebraic curves. And you're asking, how many times can an algebraic curve of degree d intersect my compact analytic curve? And this can happen. I mean, there's a uniform upper bound. For every d, there will be some uniform upper bound for the number of intersections between an analytic curve and an algebraic curve of degree d. So this uniform upper bound is exactly this constant. And this is how you get this kind of theorem. So, yes?
Maybe I missed something you said in the previous slide.
Mm-hmm.
Suppose gamma is the complement of the axis, of the y-axis.
Is the complement of the y-axis.
Correct. Then
Yes.
It is not contained.
No, I mean, this is only when our gamma is an image of the unit interval. So it's an analytic curve. It cannot be something of dimension 2, for example.
So I missed it from the previous slide. Okay.
No, the previous slide was for general sets, but here I'm talking about a result which is only for analytic curves.
Okay.
Yeah.
Okay.
But it's a good question for my next slide, because now I'll talk about going beyond. So, okay, this result kind of kills the problem for curves, because as I said, it's very general and it's the optimal asymptotic, more or less. Okay, so let's say we want to go beyond curves. We want to go to higher dimension. Then, okay, the first guess would be maybe let's take a new set and we again will suppose that it is transcendental, right? Because before, if we had an algebraic set, it was no good. Let's try transcendental sets of dimension 2, for example. Can we still expect this asymptotic? The answer is you can easily see that it's no, because even if a set is transcendental, it can still contain algebraic curves. You might have some kind of strange transcendental surface, but it contains a curve. And even this curve by itself can already contain a lot of rational points. So really, to be able to answer this question, you have to not just assume that the set is transcendental, you have to throw out everything algebraic in the set. So for this purpose, we define the algebraic part to be the union of all positive dimensional connected semi-algebraic sets contained in A. So basically all algebraic curves that are living inside the set. So in your example, if you just remove the axis, every other point is an algebraic curve, so the algebraic part will be everything. But we will talk only about the transcendental part, which is you take A and remove the algebraic part. So this is kind of the only place where we hope to count something. Okay, we throw out every algebraic curve in the set, then we try to count in what's left. Okay, so I'll just give a little warning that this kind of algebraic part or transcendental part, they can be very complicated sets. Even if you start with a nice surface, let's say an analytic surface, like this one, then the algebraic part can be, it can be dense, it can have infinitely many connected components. So for example here, these algebraic curves lie on this surface for every rational R. So it's a transcendental surface, but it has kind of an infinite and dense family of algebraic curves lying on it. So these sets, algebraic and transcendental parts, they're very complicated. But nonetheless, we will restrict ourselves to the transcendental part and we try to count rational points on the transcendental part. Okay, and so with this restriction, there is a very general theorem, which is due to Pila and Wilkey, and it really kind of kicked off this area around 10 years ago. So to make a general statement, we need to restrict ourselves to some kind of tame sets. Right? Otherwise, you can take something like A is equal to Q. Okay, if you take A is equal to Q, the algebraic part will be empty because there's no algebraic curves living inside Q, but there will be many, many rational points. Okay, so you have to have some kind of tame geometric category, and the tameness comes from an O minimal structure. So I will not define O minimal structure. In fact, in my talk, I will not talk too much about O minimal structures. I will talk about analytic sets. So if you're not comfortable with O minimal structures, then don't worry, but I'll just give the kind of a general statement of the theorem. So the general statement of the theorem says that if A is definable in any O minimal structure, then this result of Bombieri-Pila extends. Okay, then you can look at the transcendental part, you can count rational points of height h, and the asymptotic will be subpolynomial, so less than constant times h to the epsilon for every epsilon. So this is an extremely powerful result. And again, it's essentially optimal. Even for curves, it is essentially optimal. Right? I said that even for curves, you cannot expect better than this h to the epsilon kind of asymptotic. So I will not prove this theorem. It would be a subject of several talks by itself. But I want to give a little idea of the proof. So what goes into this, at least, and what are the difficulties? So the basic idea is what we are doing in induction. Okay, so for example, the case of curves is essentially covered by the Bombieri-Pila, even though Bombieri-Pila was for analytic curves. But you can kind of use their results also for O minimal structures. But to do an induction, first we will cover A by images of, instead of the unit interval, now it will be by images of the unit cube. If A is an m-dimensional set, we will cover it by kind of m-dimensional cubes. Then for each of these maps, we will construct h to the epsilon hypersurfaces of some degree depending on epsilon that contain all the rational points. Okay, this is exactly the same as in the Bombieri-Pila result. I said in Bombieri-Pila we had a curve, and then we constructed h to the epsilon many curves that contain all of the points of height h. So now we are in higher dimensions, so instead of constructing h to the epsilon curves, we construct h to the epsilon hypersurfaces that will contain all of the interesting points. And then we kind of look at these intersections, then each of them will have one dimension lower, and we will continue to kind of work inductively on each of them. That is kind of how you would imagine that this induction should work. So, of the steps that I mentioned here, step 2 is relatively easy. I mean, once you know this Bombieri-Pila method. So the Bombieri-Pila method, it was originally for dimension 2, but it also works in higher dimensions. So kind of constructing these hypersurfaces, once you have maps like this, it goes in the same way that Bombieri-Pila proved their theorem. So the problem is steps 1 and 3. So in step 1, we have to take an arbitrary set and we have to parameterize it. So write it as an image of some union of images of maps. This is not so easy. For example, if the set A is subanalytic, then this could be done by the singularization, by results of Hironaka, for example. So just covering a subanalytic set by images of a unit cube, it's possible to do. The real problem is that when we try to do an induction here, we want to kind of continue inductively with these intersections. So we have to know not only how to parameterize the original set A, we have to now kind of reparameterize each of these intersections. Right, so I will intersect my set A with some hypersurface. I get a new set of one dimension lower, and I should now cover this new set by cubes of one dimension lower. And I should control the number of pieces that the number of these images. Like how many cubes do I need to cover each of the pieces? This should be uniform over these hypersurfaces S alpha. So this is a significant problem. In fact, it cannot be done really as I have written it here. You can show that it's not always possible to do it uniformly if you restrict to analytic maps. So if you try to just do what I said here, you will see that sometimes as your family of hypersurfaces degenerates, you will need more and more analytic maps, and eventually there is no uniform upper bound for the number of maps that you need after you do one step of the induction. So that is why there is some kind of heavy machinery that goes into here. You have to replace these analytic maps by CR smooth maps, and you have to kind of show some kind of parameterization result for these CR smooth maps, and this can be done. This is really the work that Pila and Wilkey did. So they generalized a result of Yomdin and Gromov about parameterizing sets by CR smooth images of unit cubes, and then you can kind of complete the induction as it is written here. So I just wanted you to have a vague idea of how this proof goes, but I will talk about something slightly different.
Is it clear that you can cover it by finitely many images?
So, for example, if A is a subanalytic set, and you can kind of desingularize it, you can write it as an image of just a smooth thing, and then upstairs it's compact and you just cover by finitely many points. But then you have to do it in families, and it becomes much harder to show that you need finitely many and uniform over the family. Okay, so I want to give a little application just to show why this subject became kind of hot, why people started to be interested in it. So the application that I will give is kind of a baby version of the Manin-Mumford conjecture. So we will look at the torus viewed as a multiplicative group, and well, a point in the torus will be torsion of order k, if the kth power of p is the identity element. And then I let V be some algebraic curve defined over Q. So this over Q part, it's not really crucial, but I'll do it over Q just to simplify the presentation slightly. But everything I say basically works without this assumption of the curve being over Q. So what is this Manin-Mumford conjecture for the baby case that I will talk about? So suppose now that V is not a translate of a subgroup. Okay, this curve is not an algebraic subgroup of the torus. Then the claim is that V can contain only finitely many torsion points. Okay, so first of all, if V is a subgroup, then this would certainly be wrong. Like, take any subgroup for the torus, and of course it has its own torsion elements. There will be infinitely many of higher and higher orders. Okay, so kind of this restriction is necessary. We have to rule out the case of algebraic subgroups. Now the general Manin-Mumford is something in this spirit, but in higher dimensions, and you consider not only curves, you can consider general subvarieties of products of tori and abelian varieties. And the general conjecture was first proved by Raynaud, and then later it was reproved by Pila and Zania. So I will kind of just sketch the proof by Pila and Zania. But the interesting thing about the Pila-Zania proof, which was around 2008, I think, is that it kind of follows this very general structure, which was later used to prove other results. For example, the same kind of proof was used to prove the Under-Oort conjecture for products of moduli curves. And this was really new. So kind of here it was a new proof of a result of Raynaud, but it introduced a method which was then used to prove really new things. Like, for example, the first unconditional proof of the Under-Oort conjecture for modular curves. So how does this work? It's a one-slide proof. So I start by looking at this map from the unit cube to C star 2. Okay, this is just exponentiation in each of the coordinates. So the idea when we set up this map is that we are looking for torsion points in C star. They would correspond exactly to rational points in the pre-image. Right? I mean, a point is this kind of point, e to the 2 pi s. It is a torsion point. It's the root of unity if and only if s is a rational number. Okay, so now we take our curve v and we pull it back by this pi minus map. We get some subset A of the unit cube. And the rational points on this subset are exactly the torsion points that we are interested in. We would like to show that there's finitely many rational points in A. So it's not still quite clear how it connects to this, what I was talking about, because I was talking about asymptotic estimates. But I was saying, for a given height, we have this many rational points. The Manin-Mumford conjecture for this case really says there's finitely many rational points in A. And that is what we want to prove. The rational points in A are the torsion points. So the first thing that I will not do is that you can look at the algebraic part of this set. You can ask, when do I have algebraic curves in this set A? And you can show that it will only have an algebraic part if V is a subgroup or a translate of a subgroup. So it's very clear that if V is a subgroup, then A will be rational. So here's an example. If V is a subgroup like this, then A will be just defined by linear relations. This is essentially all you can have. So having an algebraic part in A, it means that x and y are related by some algebraic relation, and also log x and log y are related by an algebraic relation. So it's not hard to analyze this and see that it only happens when V was in fact a subgroup. Okay, but I will skip this part. Okay, then how do we proceed? Let's take a point in V which is a torsion point. And I will write H for the maximal torsion order among the two coordinates. So P will have at least phi of H Galois conjugates, where phi is the Euler torsion function. Right? I mean, P is a root of unity. Each of its coordinates is a root of unity. We know how many Galois conjugates the roots of unity have. Right? So they have many Galois conjugates. They have exactly phi of H, and this phi of H is more than H to the 1/2, for example. In fact, it's more than H to the 1 minus delta for any delta. So as soon as you have one point with this order H, you have to have many of them, more than H to the half of them. Okay? Now, all of them are still going to be in V, because V is invariant under, I said V was defined over Q, it is invariant under the Galois conjugation, so all of them are going to be in V, and all of them will still have the same order, because Galois conjugation doesn't change the order. So it means that as soon as we have one point like this in V, all of them are going, there's going to be like H to the 1/2 of them at least in A, and all of these preimages are going to be rational of height H, because they are all roots of unity of order at most H. So the conclusion from this is that once V contains one point like this, it has to contain H to the 1/2 points. On the other hand, we know that this set A, we said that it doesn't have an algebraic part, unless V is a subgroup. So this Pillow-Wilkey theorem applies. So it has at most C times H to the 1/3 rational points in it. Instead of 1/3, I could have put any epsilon. I chose 1/3 because it's less than half. Okay, so you have here two contradicting things. It should contain B to the B times H to the 1/2, but it's also at most C times H to the 1/3. So we see that as soon as H is too big, you just cannot contain any points of height H. And in fact, you cannot contain any points of height more than this. So this tells you that this gives you an a priori upper bound for the height of any torsion point in V. It means in particular that there have to be finitely many of these torsion points. Okay, so that's how the proof goes, and that's how many proofs of Aver-Diophantine statement go. So you have kind of the two competing sides. You have something coming from Galois theory, some lower bounds for the size of Galois orbits. Here it was just classical stuff, like the number of Galois conjugates of a root of unity. But there's similar things for torsion points in abelian varieties. There's similar things for singular moduli on modular curves. So in various circumstances, you have some reason to know that a point has many Galois conjugates. And then on the other side, these points all correspond to some rational points, and you have an upper bound on the number of rational points. And this kind of fight between these two estimates give you the result. So, okay, so what else can we kind of hope to do? Because Pillow-Wilkey is extremely general, and it's basically optimal, so what could you hope to achieve more than that? So one thing is effectivity. So for example, before I gave some kind of bound. I said eventually there's like square root of the 6th square root of C over B or something. I had an upper bound for the torsion. If we actually knew this constant C, then we could give an upper bound for the number of torsion points. That is an interesting question that people have studied. So in the general Pillow-Wilkey theorem, there is no hope to get it because it's a theorem about arbitrary analytic sets, arbitrary O-minimal structures. You cannot get effective information from it. So if you could compute this constant, it would be quite useful for Diophantine applications. Another thing you might hope for is to have better bounds if you have more natural geometric structures. So I said before that you can have really roughly h to the epsilon rational points. So you cannot improve this asymptotic in general. But this is for some kind of examples that you really tailor-make them by building some lacunary series or something. So let's say I only define my sets using e to the power z, like I did in the previous slide, or using some other kind of natural functions. Then maybe there could be much better bounds. Okay, so both of these directions are kind of interesting, and many people study them. I will not read out all the names, but and I'm sure it's not an exhaustive list. But I do want to talk about one kind of prominent conjecture in this spirit, which is the Wilkey conjecture. So Wilkey conjectured the following. He conjectured, suppose A is definable in Rexp. So it means we don't allow arbitrary O minimal structures now. We don't allow even arbitrary analytic curves. We only allow things that are definable using exponentiation plus the usual ring operations and logical connectives and quantifiers. Then, in fact, Wilkey conjectured that the asymptotic should be polylogarithmic. So much, much stronger than just sub-exponential. Not just h to the epsilon, but some fixed power of log h. Okay, so this is much harder. And only, so it's known for curves, I would say almost general. I mean, for curves that are defined without quantifiers, maybe it is known. It is known for some special cases of surfaces. But in general, it's widely open. And it also has it gives some new Diophantine applications. I mean, if you had a conjecture like this, it could give some new Diophantine applications that I will not have time to discuss. So now I will present the main result of this talk. So instead of looking at Rx, let's look at only restricted elementary functions. So that means I will not take the whole of exp. I will take exp and I restrict it to the unit interval. And I'll take also sine and restrict it to 0 pi, for example. Okay, so this is called the structure of restricted elementary functions. It's not crucial here the intervals that you choose because there's a product rule for sine and for exp. So once you have this, you can define exp and you can find sine on any compact interval. Okay, so it's just some random selection that I made there. So this structure is, you could call it, you could make a Wilkey conjecture for this structure. So let's talk about things that are definable in this structure. And then this would be kind of a restricted version of Wilkey's conjecture because we only allow restricted exponentiation. And the main result that I want to present in this talk is a theorem joint with Novikov that the Wilkey conjecture does hold for this structure. So if you just take restricted elementary functions, then there is a polylogarithmic bound for any definable set. And moreover, it is kind of effective. So we computed this constant kappa. I will not write out the formula because it's complicated. And this C we did not compute, but everything is computed. So we didn't bother to go through all the computations, but you can compute both kappa and C from the proof. There's nothing kind of non-constructive in this proof. Okay, so I'll give really a rough idea of the proof. So the main thing was that we couldn't handle these parameterizations. I said that the really hard part of the Pila-Wilkey theorem is you need to build these parameterizations by CR smooth functions, cover things by unit cubes. And that is a very difficult and technical part of the proof of the Pila-Wilkey theorem. So we developed some kind of alternative approach which uses a more holomorphic structure. So first we complexify A using some quantifier elimination result of Van den Dries. So we show that you can kind of embed A in a complex analytic variety. Then for complex analytic varieties, we showed that instead of parameterizations, you can replace it by kind of analyzing the complexification. So I really have no time in this talk to show how this is done, but kind of instead of covering by images of the unit cube, we need to kind of look at some pieces of this complexification. We restrict to some part where the complex analytic geometry is good, and then we can kind of repeat these ideas in the style of Bombieri and Pila, but without using parameterizations. And this was really kind of the major stumbling block for the proof. And then the last part is we need to somehow effectively estimate the complexity of this complexification. Right, so we complexify, we got some new varieties defined by equations involving these restricted elementary functions, and then we have to analyze something about them. So the first two steps don't require anything about restricted elementary functions. In fact, steps 1 and 2 that we make here, they prove the Pila-Wilkey theorem for subanalytic sets. So they give kind of a much simpler proof if you're willing to restrict to the complex analytic setting. However, for the third step, if you really want to get polylogarithmic bounds, you have to somehow analyze the number of solutions of systems of equations involving restricted elementary functions, and this requires that you use much more. And if you need to use more structures somehow, it's just not true for general analytic structures. So for example, we need to know that if you take a curve which is defined using these restricted elementary equations, take some curve which is defined by equations that you cook up with exponentiation and with sine, just cook up a system of equations. Then let's say that you intersect this curve with an algebraic hypersurface of degree d. We need to know that the number of solutions will grow polynomially in d. Okay, this is the kind of thing that we need to know. So something like the Bezout theorem, some estimates for the number of solutions of systems of equations. And this is where differential algebra comes in, or differential equations.
But
Yes?
third part work for other Fuckin functions?
I will say something about that in one more slide. So first of all, I'll say what we used. So we used the fact that the restricted elementary functions, as well as their complexification, is Pfaffian. So Pfaffian means that it can be, these functions can be expressed as polynomial combinations in solution of a triangular system of algebraic differential equations. So here I show this for x and for sine. So you see this equation, it only involves E. This the tangents only involve tangents. This equation for cosine, it involves tangents which was already treated, and cosine, and finally equation of sine uses cosine. So it needs to be triangular like this, a kind of an upper triangular system. Now when you have an upper triangular system like this, then there is a well-developed theory of solution of systems of equations. So this is called Chovansky's theory of few nomials. Okay, so as called Chovansky in the early 80s, he showed that whenever you have triangular systems like this, then there is a kind of Bezout theorem that allows you to control the number of solutions of systems. In fact, we need a little bit more because we are dealing with definable sets. So we need not just systems of equations. We need to deal with inequalities. We need to deal with projections. But this theory of phenomena was extended to semi-Pfaffian and sub-Pfaffian sets. So it means you can allow also equalities and inequalities, and you can allow projections, and still you have good estimates for the complexity. And this is by various people, but I'll mainly mention Gabrielov and Vorobyov, who wrote many papers about this subject. So this is kind of the extra ingredient that we use. So it's natural to ask, well, okay, restricted elementary is one case of Pfaffian functions. What about other Pfaffian functions? So I'll make two notes. One is that it's not enough that the function is Pfaffian. Here it was kind of a miracle that the complexification was Pfaffian. Okay, so E is Pfaffian. If you look at E in the complex domain, you also need sine and cosine, but also sine and cosine are Pfaffian when you restrict to a strip. So if you just take an arbitrary real Pfaffian function, probably the complexification will not be Pfaffian in this sense. We need functions that are viewed as complex functions that are still Pfaffian. And one last slide about some future directions. So, for example, if you look at elliptic and abelian functions, they are still Pfaffian in this sense. So you can write them kind of as integrals of some algebraic one forms on your elliptic curve or on your abelian variety. And as such, they satisfy Pfaffian systems of equations. This was, I think, first kind of noted in the work of McIntyre. So using this kind of idea, we can, instead of restricted elementary functions, we think we can also deal with elliptic and abelian functions. There are some small technicalities we still haven't written down, but it appears that this method will work also for elliptic functions and abelian functions. And these are the kind of functions that you need if you want to do a general proof of the Manin-Mumford conjecture. Because Manin-Mumford is about product of abelian varieties and tori. Okay, so you need also these abelian functions in order to handle general Manin-Mumford. Now, it would be reasonable to think that you should have the same kind of thing also for modular functions. So for example, for Klein's modular invariant J, which is used in Pila's proof of the Andre-Oort conjecture, or you could ask about automorphic functions of other Fuchsian groups, which are associated to some Shimura varieties, and they're also important in Diophantine applications. So the first two steps of the proof probably work. The first two steps, as you recall, I said they work for kind of arbitrary analytic things. The really problem is how to analyze the number of solutions of systems of equations. And this step doesn't work because modular functions are not Pfaffian as far as we know. Maybe somehow you can express them using some big Pfaffian chain, but we are not aware of any results in this direction. So that is why this method that I describe now will not prove a kind of a Wilkey conjecture for modular functions, at least not yet. However, I will make one final note that modular functions do satisfy some algebraic systems of differential equations. They're not Pfaffian anymore, they're kind of Schwarzian equations. The Schwarzian of a modular function usually you can express as a rational function or something like that. So you have a higher order equation, and it's not Pfaffian, but there is some algebraic structure to it. So if you are looking for, example, effective estimates of this Pillow-Wilkey constant, or even if you're looking to prove a Wilkey conjecture, then I would say a reasonable place to start would be to analyze these systems of differential equations and try and get something like Chovansky's theory of few numbers for these types of equations. Okay, getting the general Wilkey conjecture is quite optimistic. I don't see a path right now how we can do it. But getting effective estimates for this constant, which would yield significant Diophantine applications around the under-Roth conjecture, this is, I think, quite doable. So there are some results about counting zeros of equations of this type, and I think we are quite close to getting an estimate for this constant. And probably furthering to get better analysis and maybe get something like the Wilkey conjecture, probably we would need to understand something more about these differential equations, how to use their symmetries. So they're highly symmetric, these equations. And differential Galois theory of these equations enters the picture, but in some way that I will not have time to describe. So okay. That's everything I want to say. Thank you very much.
Questions? When you say you get computable bounds in this, does that include the quantifier elimination, or is this after the quantifier elimination?
We get it after the quantifier elimination. In fact, our method, we think, should also make the quantifier elimination effective. But we haven't done the quantifier elimination part yet. For the Diophantine application, in fact, you never use any quantifier. So it's always kind of systems of equations. But we have thought about and also seeing if we can make the quantifier elimination effective.
Any other questions? Let's thank